Okay, we're now going to switch gears. This is still section 6.2. Section 6.2 has a lot of different content. The first part of it, which is now concluded if you're watching these in order, and that was all about volume integrals. So we are going to, it's the idea that if we integrate cross-sectional area, we will get volume. Well, now we're going to sort of abstract from this a little bit, and now we're going to talk about what do we get if we integrate something that doesn't necessarily have the units or physical interpretation of an area. What else are integrals good for, in other words? So here we're going to start with density. So integrating a density. So for this first setup that we have here, this definition, we'll see the word is a linear mass density. So what this essentially means is it doesn't have to do with the function is a linear function. It just means that it tells us the density as we move in one direction. So our density our density function rho, may very well be a nonlinear function. It doesn't have to be something of the form mx plus b as a first degree polynomial. So linear just means that as we move in a certain direction, the density potentially is changing. So if we think about a certain x value, the density is changing only if we change that x value. So the density is the same at this point here, as it is here, as it is here. So it's only varying in this one direction. Okay, so if we know the density at any x value, what we could do is split this rod up into lots of little pieces as what was done here. So here we have n pieces, n little chunks of this rod. And as n goes to a very large number, let's say it goes to infinity, then each of these little pieces is extremely, extremely small. This width here, delta x, is very close to 0 if n is very, very, very large. So what this means is, true, the density is different here on the left end than it is here on the right end. And potentially it's different at every intermediate x value. But if this width, delta x, is very, very small, then the difference between the density here and here has to be very, very small, provided that the density varies continuously. If the density doesn't vary continuously, then there could be a very large difference. Okay, but let's just say it varies continuously. So then what we can do is, although the densities are different at the two ends, we can effectively just say the density of this first little piece, we can just approximate it to say that the density for throughout the entire piece is the same as the density at just this farmost x value. So if we were to take this back to the x-axis, we would say that the density of this chunk here is just the density at this x1 value. And that for the second chunk here of the rod, we would say the density is the same throughout, and it's equal to this x2 value. Okay, so if we know our density, so let's say our density is something that varies with respect to length. So our density function, rho of x, this would be the density. So this would be measured in kilograms, let's say, per kilograms per meter, something like that. And what we're going to do then is figure out the total mass by integrating. So I want to finish this sentence. Sorry, I got a little distracted myself. Rho of x is the density measured in these units at x meters. So what does the integral over some range of values of this density function look like? What does this tell us? Well, the nice thing about an integral, a definite, or not even a definite integral, just an integral, is whatever your input units are. So our input units are kilograms per meter. We take that and we will multiply it by the units of x. So you can interpret this rho of x dx as a product. So we'll think about the units of rho times the units of x, or the units of dx. Since dx is just an infinitesimally small change in x. So the units of x are m, so the units of our final answer should be units of kilograms only. So effectively, this gives us mass. So we can go ahead and summarize this succinctly as saying mass, or let's say total mass, is the integral of density. All right. So we can take a look at example 7 as well. Determine the total mass of a 2-meter long rod whose linear density function is rho of x equals 1 plus a half sine of pi x kilograms per meter. Okay, so what we want to do to find the total mass m, we would integrate from 0 to 2 and our density function. So 1 plus a half sine of pi x dx. So this is x minus, because sine integrates to negative cosine, so this would be minus 1 over 2 pi cosine pi x between 0 and 2. So 2 minus cosine of 2 pi is 1. So this would be 2 minus 1 over 2 pi minus everything with a 0 plugged in. So 0 minus cosine of 0 is 1. So 1 over 2 pi. So this should simplify down to what? We have a minus 1 over 2 pi, but then double negative, so plus 1 over 2 pi. So these cancel, and we're left with just 2. And of course the units here, they are given, so this would be 2 kilograms total.